Okay, welcome to lecture 6. I am going to continue on with the topic of causality. We have a few more ports to investigate and set up some rules for their input-output relationships for the effort and flow. We closed lecture 5 determining the derivative causality of the inertia port. And I have that displayed here as the last piece. Just to finalize that, the derivative causality of the inertia port is when the causal stroke is to the not adjacent to the eye, and that gives us that the flow is the input to the eye. So in my block diagram here, I have a flow that is input into the eye, and to get from that flow to the intermediate variable momentum P, we have to apply the constitutive law. So I apply this constitutive law, I get the variable P, and then relationship from P to get us to E is that I take the time derivative of P. dP dt equals E. You can remember that as the time derivative of the momentum has to equal the sum of the forces, right? We have that effort and momentum relationship. So here we have the flow input to the effort output relationship, and then I wrote the equations here to the right that would represent those with the E as the output and the F's as the inputs. All right, so remember that causality is the input-output relationship between the effort and flow for a given port, and it tells us which way we write the equations that define that port. So let's move on. Let me go to the next lecture here, deck. We just covered the one ports. So there are causal rules for the 2 ports as well as the 3 ports. These are pretty straightforward. So let's look at those. We'll start with the 2 ports. Each of these 2 ports have 2 possible causal rules. So each has 2 possibilities. Okay, let's start with the transformer. The transformer looks like so. And we have a E2 and an F2. So for the transformer, if I apply a causal stroke on the left side, like so, that means that the flow then is the input here to that transformer, and the effort on the left-hand side would be an output. For the transformer, I have to apply then also on the left-hand side the causal stroke for the to side, which sets this up such that the flow is the output of the transformer, like so. So the way to see this is that for a transformer, the flow, if the flow is an input on the left side, it has to be an output on the right side, and then the same for the effort. If the effort is an input on one side, it has to be an output on the other side. So this is one possibility for the transformer. The equations then we would write as our effort 1 is an output of the transformer. So then we have our constitutive law such that the E2 is the input. And then similarly, we would write that F2 is an output with F1 as an input. So these are inputs to the transformer, and these are our outputs. Similarly, we can have another scenario. If the causal stroke is like so, then for the one side, then the two side will have to be as drawn. So that just swaps the inputs and outputs, and then we would see that E2 is now the output, and we would write our equation like so, and F1 is the output here. So we have our inputs and outputs. Those are the two possibilities for the transformer, and if an effort is an input on one side, it has to be the output on the other side, and same for the flow. Right. So the gyrator also has two possibilities. The gyrator, if I apply a causal stroke on the one side like so, then the causal stroke on the two side must be on the left side of that bond. And this shows us that the gyrator relationship for the inputs or outputs, right? If I have this E1 as an input, the other E2 also has to be an input, right? And then the flows are both outputs. Then I can write the equations. There's F1 is going to be 1 over R E2, right? So F1 is an output, E2 is an input, and F2 is also an output, 1 over R E1. So once again, our inputs and our outputs. And then lastly, the gyrator. The other option is that both of the causal strokes are to the outside of the two-port there. And this means that both flows then become the inputs and both efforts become the outputs. And we can write our equations. Yeah. So the gyrator has this relationship between the efforts and the flows that set up this input-output connection, where a flow input will make a effort output, and vice versa. Effort inputs are going to make flow outputs. Right? So you can see how the gyrator is sort of the inverse of the transformer. So those are the causal possibilities for the transformer and the gyrator. Right? So the transformer has to have the causal strokes both on the left or both on the right, as I've drawn them, and the gyrator has to have them both to the inside or to the outside for the options there, and they will give us those equations. All right. So that's the two ports. Pretty straightforward. You can put either option when you are setting up your bond graphs, and we'll see that in action as we move forward. The last one here is to look at the causality of the three ports. So this is 3 ports or more, as we've defined. The rules apply the same. Okay. So the key thing on these are that only one of the bonds on the 3 or more ports can be the input. Yeah. So let's start with the common effort junction. Right, that is a 0. And we know that all the efforts are the same and that the flows have to be summed. So if I add some bonds here, and I am going to add the signs, we're going to have to write the summation of the flows. So I want to use the arrows to set up the sign convention for that summation of the flows. Now, for the common effort, when I say only one bond can be the input, for the effort, only one effort bond can be the input. Only the effort on one bond can be the input. That's a better way to say that. And then for the flow, it'll be opposite. Only one flow can be the input to that particular port. So for example, if I say that the effort 1 is the input to this port, the effort, right, input, that means that none of the other bonds can have a causal stroke adjacent to the O. They all have to then be on the outside. Right, so this gives me one effort is the input to that 0 junction, and the other two are the output. Now that means that for the flows, that is opposite. We have many flow inputs and only one flow output. So what does that look like in terms of the equations? Well, E2 is an output, E3 is an output, and they are both equal to E1. And then for the flows, we see that flow 1 is an output, and flow 1 is the two inputs for that equation are going to be flow 2 and flow 3. So this one ends up being minus flow 2 and minus flow 3 for the sign convention there. Right? We know that all of the arrows are pointing in. So if I wrote them all on the left-hand side of the equation, they would all have the same sign, F1 plus F2 plus F3. And then if I rewrite it so that my inputs are on the right-hand side, I will get these two negative values that match for the half arrows, right? The signs of that summation are tied to the half arrows. The causal strokes, though, are what sets all of these pieces to be the inputs. And then we have written the 3 outputs there. Okay? The key thing, only one bond effort can be the input to a common effort junction. And then if we look at the common flow junction, where all the flows are the same, we have the same rule, but only in terms of the flows. Right. So I'll just add the same signs here. I just have them all pointing in. So we'll get the same sign, but this will be for the summation of the efforts, right, since the flows are the same. I will make F1 my sole input to the junction, sole flow input to the junction, and that means that the other two have to have the causal strokes adjacent to the one, and that will set these up to have the two E's are going to then be inputs, and those two F's will have to be outputs. So we have one flow input to the one junction, and then we can write our equations. We know that F2 is an output, and it is equal to F1, common flow junction. F3 is also output, equal to the input F1. And then we make a summation. We see that E1 is the output, and it is negative E2 minus E3. All right, so E2 and E3 inputs to the one, E1 output of the one. We have our same setup here. This side inputs, here outputs. Okay, so there's only one causality possibility for the 0 and the 1, and for the 0 we can have one effort can be the input, and for the flow we can have one flow can be the input. So once you set one causal stroke, no matter how many port bonds you have on this particular port, 3 or more, you will have set the causality of that entire port. Right? So that concludes the basics of causality. There are these rules for the causal strokes for each of the ports that you have to follow. Some of them, for example, the source flows and efforts and the ones and the zeros, there's only one possibility for setting up the causality. For the I, R, and C, there's two possibilities, and for the I and the C, we have called them, those two possibilities, integral and derivative causality, due to the intermediate step to get to either the displacement Q or the momentum P variables. And then the two ports, they have two possibilities too, that we've shown here. So that's all it is for the causality. You need to be able to know what causal strokes are allowed for each port, and then once you see a port with that particular causal stroke, can you write the equations in the form that has the inputs on one side of the equation and the sole outputs on the other side of the equation? And that's it. That's causality. So that is the end of this. In the next lesson, we will move into actually setting up and creating some bond graphs.